Hello and welcome back to College Algebra. Today we're going to be talking about Section 5.2, but a quick reminder, homework and quiz number 11, which contains sections 5.1, 2, and 3, is due Tuesday, April the 14th at 11:59 p.m. Central Standard Time. Please remember you do have to have at least 75% on your homework before your quiz will open up. Let's get started with Section 5.2. So Section 5.2 is our beginning section on logarithmic functions. Logarithmic functions are the inverse functions of exponential functions, and we talked about exponential functions in Section 5.1. The notation for a logarithmic function looks like this. Y, or we could use f of x, is equal to log base b of x. That's how we read that. This is only true for x values that are greater than 0. That would be our domain for the function. And also values of b, our base, which are greater than 0 and not equal to 1. We saw something very similar to this when we talked about exponential functions in Section 5.1. The expression y is equal to log base b of x is equivalent to the expression b to the y is equal to x. If you recall, when we talked about inverse functions, one of the things we talked about was we could swap the x and the y. So logarithmic functions and exponentials are inverses of each other. So the value of the logarithm becomes the exponent for the base. The x here becomes the value of the exponential expression. So we'll take these two and we'll rewrite exponentials to logarithms and logarithms to exponentials, and we will do that several times. So recalling that this expression, the exponential expression b to the y is equal to x, is equivalent to y is equal to log base b of x, just flipped it around from the previous page. We want to take each of these exponential expressions and rewrite them into their equivalent logarithmic forms. So let's examine 3 to the second is equal to 9. In this case, we can identify y as 2, b as 3, x as 9. And so if we put those in the appropriate places, y being 2, so 2 is equal log base b is 3 of 9, that's my x value, and this is our equivalent logarithmic expression. We could also write the logarithm part first, so we could write log base 3 of 9 is equal to 2. I think one of the key things in logarithms is to always remember that the logarithm is equal to the exponent. So the value of the logarithm is always an exponent when we rewrite it. Okay, let's do the same thing down here for number 2. So we're going to start with our y, which is our exponent. That's what our logarithm will be equal to. So negative 3 is equal to log base for my exponent is 2, that's the base for my logarithm, and 1/8 is the only number that I haven't put somewhere, so sometimes that's helpful also. Okay, so the other option is to write the logarithm part first, so log base 2 of 1/8 is equal to negative 3. Notice that this base is slightly below the logarithm. It's a subscript. So be careful. Alright, this last one here, we're going to do exactly the same thing. We have an expression now for y. So 5 times k is equal to log base 7 of L. And we could again write this as log base 7 of L is equal to the value of 5 times k. Right? So now we're going to flip-flop this process. We're going to start with the y is equal to log base b of x, and we're going to rewrite it into the exponential form. B to the y is equal to x. Notice that this is written actually in the form of log base b of x is equal to y. So just flip-flop the two sides of that equation. That might help a little bit in terms of identifying. So what we want to identify first is the base. So 5 is going to be my base. So I have 5 to the, and what the logarithm is equal to is the exponent for my base, so 0. So 5 to the 0 is equal to 1. And that's my final answer. I don't want to do anything else. You do know that 5 to the 0 is equal to 1, so it's kind of a nice way to check and make sure you're doing that correctly. Same thing on number 5. Identify your base for your logarithm. That would be 4. 4 is raised to the power of the value of the logarithm, so 4 to the L is equal to K. Right? And one final problem, this one does involve an expression here, still identifying the base first, so a to the third power, because that's what the logarithm is equal to, and then we have our expression x minus 1. You can put that in parentheses or not, it's not going to make a difference. And so these are my 3 answers. All right, so now we're going to talk about how to evaluate one of these expressions without using a calculator, because while your calculator will do some logarithms, it doesn't do all of them. So I told you a while ago that the value of the logarithm is my exponent, and so what I'm going to do is I'm going to be thinking about b to some power is going to be equal to my x value. So if I can think through that process, so when you evaluate these, you ask the question, 2 to what power is equal to 8? And that power is going to be the value of my logarithm, and that's going to be 3. So 2 to the third power is equal to 8. That's how we will evaluate these. You could have done 2 to the y is equal to 8, and then said, all right, y must be equal to 3. And then that goes there. Okay? So let's do number 8. So 3 to some power is equal to 1 over 9. I know that this power must be some kind of 2 because 3 squared is 9. But in order to turn a whole number into a fraction, you guessed it, I have to have a negative number. So this value is negative 2. 3 to the negative second power is equal to 1/9. Now this one's a little bit harder, so I'm actually going to rewrite this one before we try to evaluate. Those cubed roots, we just like to rewrite those as an exponent. So the cubed root of 6 is the same thing as 6 to the 1/3 power. We've talked about these before. So now I can ask the question, 6 to what power gives me 1/3? And my answer is going to be 1/3. So here's the question I'm asking. 6 to some power is 6 to the 1/3. And that exponent must be this 1/3. And this is going to be my value. All right, this one is a little bit harder. So again, we've got a whole number turning into a fraction. We're asking the question, 4 to some power is equal to 1 over 64. So hopefully you'll recognize that from this previous problem over here, number 8, that my exponent has to be negative, exactly. So 4 to what power is 64? Well, that would be 4 to the third power. It has to be negative because I'm taking this whole number and I'm turning it into a fraction. And so my final answer is negative 3. Excellent. Let's talk about a couple of just special properties that help you out just a little bit. So if you learn these special properties, you don't have to go through all of the process that we did on the previous problems. So this first special property, these are all called cancellation properties. If my base for my logarithm and the base for my number match up, then they essentially cancel each other out and leave me with 1. So the log base 5 of 5 is going to be 1. Doesn't matter what my base is and what my value is, if these two guys are the same, they cancel out. The next cancellation property is an extension of the first one. So think of this as b to the first power, so now we have b to the x power. Again, because they are inverse functions, that's what allows them to cancel out. If you recall, if I take the square root of x squared, and I know that x is a positive number, I'm going to get x, so things cancel out. Same kind of thing happens here. So log base 7 of 7 to the negative 4th, you guessed it, is negative 4. Okay? For number 13, we're going to use the third cancellation property, where I have b to the power of a log base b of x. Again, my base for my exponent, and my exponent is a logarithm, so the exponent and the logarithm cancel out. So I'm going to be simply left with whatever number is here. So in this specific case, we have 2 to the log base 2. Those are the same. Of 11 is simply going to leave me with 11. And then the final cancellation property, if I have log base b of 1, then this is always going to be 0, because I'm really rewriting this. If I were to rewrite this in exponential form, b to the 0 is equal to 1. That's the only exponent I can have there, and so this value has to be 0. So these little properties will just help you out on the homework, the quiz, and the test, and as we move through this section on exponentials and logarithms. Now, we also have some very special logarithms, and those are our common logarithm and our natural logarithm. The common logarithm is when we have a base of 10, because our entire number system is based on the number 10. So if you have a log without a base, that base is understood to be 10. So you could, in theory, write this as log base 10 of x. You will not see it written like this, but if you have a logarithm with no base, that base is understood to be 10, and we call it a common logarithm. The natural logarithm has a base of e, and if you recall in section 5.1 we talked about e being Euler's number, and so rather than writing this as the log base e, somebody decided we needed another kind of notation, so log base e became natural logarithm, or ln. It looks kind of like an in on your calculator, but that's why the second or the inverse function of ln gives us this e when we were working problems the other day. So some special cases, the natural log of 1 is always 0, the natural log of e, because my bases match up, is always 1, and the natural log of e to the x is always going to be x. This is because the base for my logarithm is e, and my base for my exponent is e. They match up. Okay? So we're going to simply take these two problems and put them into their logarithmic form. So I'm going to ask you to recall that b to the y equals x can be rewritten as y is equal to log base b of x. That's what we're going to be using here. So my exponent here is 3. So 3 is going to be equal to log base 10, but remember we're not going to write that 10, so log base 10 of 1000. And that's our final answer. You could put your logarithm first, so log base 10 of 1000 is equal to 3. All right? We're going to do the same thing here with our natural exponential base, so we'll rewrite this as a natural logarithm. Again, my y or my exponent is k, so I'm going to start with k is equal to log base e. Just got through telling you log base e is this natural log, and then we have of 2. So k is equal to the natural log of 2, or again, we could write this as the natural log of 2 is equal to k. Right? Very good. So these problems we're going to be writing in, if you can see this, we're going to write the following logarithms in exponential form. So again, I'm going to just remind you of our general format. log base b of x is equal to y is an equivalent expression to saying b to the y is equal to x. And this is the form we're going to come up with. So in this case, our base is the first thing we need to find. And what is the base here? Yes, it's a base of 10. So we have 10 to the L power is equal to K. Please be careful in MyLabs Plus, anytime you're writing these variables, it does make a difference if you capitalize them or use lowercase, and both of these are lowercase letters. Most of these are, but just be aware of that, okay? All right, let's do the same thing with number 18. Identify your base. The base for the natural log is e, and so we have e to the 4 is equal to z. Excellent, very good. All right, we're going to do one more thing with logarithms in this lesson, and that is to find the domain of these logarithmic functions. So if you recall, the range for your exponential functions from 5.1 was positive numbers, 0 to infinity. And I also told you on the very first page of this set of notes that if you have the equation y is equal to log base b, it doesn't matter what, of x, x had to be greater than 0. So it ties into the range for our exponentials. So we did some similar problems to this when we talked about the domains of square roots functions, and we're going to do the same kind of thing here, except we don't want it to be equal to 0. So to find the domain, we take whatever expression is here. So in this case, negative x, and we set it greater than 0, and we solve for x. Now if we multiply or divide both sides by a negative number, remember, that means that I have to change the direction of my inequality. So positive x now becomes less than, and 0 times negative 1 is still 0. Let me put this in here. So we're going to multiply both sides by negative 1, and that's what gives us positive x is less than 0. Okay? All right, let's do the same thing here for number 20. It does not matter. The base on this one was 10. The base on this one is 1/4. It does not matter what the base is. That is not going to affect the domain. So again, we're going to take this expression, so 2x plus 6, and we're going to set it greater than 0. Subtract 6 from both sides, so I have 2x is greater than negative 6. I did not multiply or divide by that negative, so I do not change the direction. I'm going to divide by a positive 2, so it still says greater than, and this is going to be greater than negative 3. Going back real quick here, if I wanted to write this in the interval notation, remember this is negative infinity to 0. And this interval notation is negative 3 to positive infinity. Notice I use round brackets on everything because it's not ever going to be equal to that value. Okay? The last one of these for our domain is the natural log of 1 minus 3x. Again, my base is e, but that does not affect my domain. So I'm going to take the expression in here, 1 minus 3x, and I'm going to set it greater than 0. I'm going to solve this inequality. Negative 3x is greater than negative 1. Let's move over here. Negative 3x greater than negative 1. Divide both sides by negative 3. So I'll actually write that in here so you can see what's happening. Dividing by this negative is what causes that inequality to turn around. This becomes x now is less than negative 1 divided by negative 3 is going to be positive 1/3. And so in an interval notation, my domain is negative infinity to positive 1/3. And that's the end of section 5.1. I hope you have a great day.